Okay, so we're going to kind of continue our discussion of two connected graphs now. And actually, I really want to go back to the definition of two connected graphs because we're going to be looking at a very, very closely related definition. And anyway, it's going to be easiest if we reintroduce that definition. So, let me just comment at the start here that for the purposes of this lecture, I'm going to assume that I'm working with simple graphs. The effect of parallel edges or loops is only to add a little bit of complexity in the discussion. It doesn't add anything to what we're doing at all. So I mean, everything that we say, once I've said it for simple graphs, the same things will hold more generally, but it'll be a little bit easier to describe things just to sticking to simple graphs. So that's what I'm going to do. Now, again, our definition of what it means for a graph to be two connected, it actually has three parts, and let me highlight those. So condition one is your graph G is connected. Condition two is that for any vertex V, if you delete it, you will stay connected. So G minus V is connected for every V. I could say V and V of G to be a little bit more precise here. So for any vertex, when you delete it, you still have a connected graph. Third property is that you have to have at least three vertices. Right, so if you have 1 and 2 and 3, then your graph is two connected. Right, so again, a graph is two connected if it's connected. However, you delete a vertex, it stays connected, and you have at least three vertices. Now, we've seen in the last lesson that there are several equivalent forms of this notion of two connected. Saying the graph is two connected, it also means that for any two vertices, there's a cycle through those two, or for any two edges, there's a cycle through those two. So we have a lot of nice properties about two connected graphs. They're very well behaved things. Now, what we're going to look to today is a way of taking an arbitrary graph and kind of breaking it up into two connected pieces, or almost two connected pieces. So after we establish our notion of connectivity, just basic connectivity, we learned that, well, every graph has this natural a way of representing it. It's just a union of its connected components, right? So if you think in terms of components, then the components individually are connected, and your graph, well, if it has more, if it's not connected, then you just have some number of connected components. And that's very easy for us to understand. When we level up in connectivity, we're kind of lose a little bit of that niceness. But there is something that happens in the kind of two connected case, and that's what we're going to look to today. But in order to get there, what I want to do for a moment is just focus on what it means for a graph to satisfy just the first two properties here. Suppose I gave you a graph that's connected, and I promise you that however you delete a vertex, you stay connected. Well, this is basically, it's almost a two connected graph, right? I mean, if I just added the assumption you have at least three vertices, then I'm talking about two connected graphs. So dropping that assumption, what does it mean? It means that either I'm staring at a two connected graph, or I have at most two vertices. So if you satisfy 1 and 2, this means that either you're two connected, or you have at most two vertices. So that's actually the property that we're going to be focusing on here, and it's going to be easiest for us to understand it in those terms. So if I give you a graph that is connected and has no cut vertex, then either it's kind of a nice two connected graph, you've got to cycle through any two vertices, cycle through any two edges, so on, or it's not because you're just too small, or you've got at most two vertices in the thing. Okay. So the reason I'm focusing on this here, and I'm allowing, usually we're not that worried about graphs that only have two vertices. It's not such an exciting kind of a graph, but we're going to be looking for these things as subgraphs of our original graph. So our excuse me. So our definition here, our main definition for today is as follows. A block of a graph G So a block of a graph G is going to be a maximal connected subgraph that satisfies properties 1 and 2. So that H is connected. In fact, let me write it. Satisfying the two properties. 1, H is connected, and 2, H minus V is connected for every vertex in H. Right, so again, the properties 1 and 2 saying you're connected. However you delete a vertex, you stay connected. That is almost describing two connected graphs. You're two connected, or you're just tiny, or you have at most two vertices. Now, what we're going to be doing with our graphs is we're going to be interested in subgraphs that have these first two properties. So I'm going to give you a graph G, and we're going to define a block of G to be a maximal connected subgraph with the feature that connected subgraph stays connected when you delete a vertex from it. And now maybe I'd better, let me just make a little space up here. So I'm going to keep these this definition here, and just erase up here to give myself a little bit of space. Just keep that definition on the board for a minute. Okay, so again, a block of a graph G, it's going to be a maximal subgraph of G. Oh, sorry, the connected is redundant here. A block of a graph G is a maximal subgraph that has these two properties. First off, it's connected. Second, it has the property that however you delete a vertex, it's connected. Well, now that I even move this up. There. Okay, so here's our definition again. And let me just show you an example. So again, I'm going to restrict my attention to simple graphs here. I'm not going to be drawing parallel edges or loops because they're not going to matter for any of this anyway. And I'm going to stick to connected graphs as well. So let's okay. So there's my graph G. What do the blocks of this graph look like? So Again, we are looking for subgraphs that are going to be maximal, subject to being connected, and having the property that however you delete a vertex from them, you stay connected. Now, let's take a moment here and look at the cut vertices of the original graph. Here's a cut vertex of my original graph. If you want to make a block of G, you're not going to be able to take a vertex to the left of that black vertex and also to the right, because then those two vertices, if they're in a connected subgraph, you're going to have to contain this black vertex. But if I delete the black vertex, you're going to disconnect it, right? This black vertex disconnects my original graph. So if you're looking to make a block, you're going to have to either take stuff kind of on just on one side of that black vertex, and that's true more generally anytime you see a cut vertex, right? So let me go ahead and highlight the cut vertices of this graph. These are not hard to pick out. And what are we going to see here? Well, let's now go think about our blocks. I claim that this subgraph is a block of G. So that's a subgraph. It's a 4-cycle plus an additional edge. So the subgraph, I mean, all 4 of those vertices and all 5 of those edges. That's a subgraph of our original graph. When you look at that subgraph itself, that subgraph, it's K4 minus an edge. It's a cycle plus 1, a 4-cycle plus 1 chord. That graph is a connected graph, and that graph on its own has the property that however you delete a vertex from it, it will still be connected, right? So this is a graph that satisfies those two properties, connected and still connected when you delete a vertex. And this is a maximal subgraph of my graph G, having those two properties. If you tried to make this subgraph any bigger, well, satisfying those two properties, well, if you want to make it bigger and stay connected, the only thing you can do is to add in this extra edge here, right, and that vertex, but then you'd be violating the second property. Then that graph that you create would have the property that, well, when you delete that black vertex there, then you'd be disconnecting it. So this thing that I've circled in orange is a maximal subgraph of my graph G, holding onto these two properties, connected and connected after you delete any vertex. This edge here, together with its two ends, that is another block of G. So that edge, I'm just talking about this 2-vertex graph. That 2-vertex graph, that still satisfies properties 1 and 2. So that 2-vertex graph, right, it's just an edge. It's K2. That is a connected graph, and if you delete a vertex, it is still connected. Now that 2-vertex graph, it is not a 2-connected graph because it doesn't meet the threshold of having at least 3 vertices. So this graph that I've just circled, this little subgraph, it is going to be a block in our graph because it is I've verified that it's a connected subgraph and it's connected when you delete any vertex. Also, you can't enlarge it. If you try to take this graph and add anything else to it, you'll see that the subgraph that you form is going to violate either condition 1 or condition 2. So this thing I've circled in this last edge that I've just circled here in orange, this is in fact going to be a block of my graph G. It is not a 2-connected graph, a 2-connected subgraph, because this subgraph doesn't have enough vertices. So we don't, you don't get this property, for instance, that there's a cycle through any 2 vertices. There isn't. But it is still a valid block. Let me circle the other blocks. So this is going to be a block of our graph. Ooh, well, I'll take that. Okay. This is going to be a block. This is going to be a block. Here is a block. Here is a block. And here is a block. So those are the blocks of this graph. So again, by definition, a block is going to be a subgraph of a graph that is maximal, subject to being connected, and having the property that it stays connected when you delete a vertex from it. So again, when I'm talking about those two properties, I'm talking about the subgraph itself, not the original graph. A subgraph H of my graph G is going to be a block if H is a maximal subgraph of G with the properties 1, H is connected, and 2, H stays connected when you delete a vertex. And again, when I'm talking about those two properties, I'm almost saying two connected. The only caveat is that you might just have too few vertices. So I'm a graph satisfying those two properties, connected and connected when you remove any vertex, it's either going to be a two connected graph or it's going to be a graph with at most two vertices. And so that's what the blocks of our graph G are going to look like. The blocks are going to be subgraphs that are either two connected or just going to be two vertices. Now, you'll see here that for our graph G, I indicated the cut vertices there in black, and I've indicated the blocks in orange, and you can see that there's a kind of tree-like structure to this picture, right? So the goal of today's lesson is actually to prove that tree-like structure always exists. And this is telling us about the kind of two connected pieces of our graph G. Again, when we were doing connectivity, learning about what it means for a graph to be connected, we said, well, okay, if you give us a graph that's not connected, then you can kind of break it up into these connected components. And that's a nice way to think about it. And what we're seeing here is a similar thing, kind of one level up. So if I'm giving you a graph that is, say, connected but not too connected, then you can kind of ask about the two connected pieces. And that's really asking about the blocks of the graph. And it's going to turn out that the blocks of the graph always have this nice tree-like structure. That's a very useful thing. Thinking in terms of connected components is very, very, very natural for a graph. This is a similarly really nice framework. So if you have a graph that's connected but not too connected, we can really understand in what sense it's not too connected and what the two connected pieces of that graph are. It's really very, very, very transparent in this form. It's basically a tree. Your graph is basically a tree-like structure of subgraphs that are either too connected or almost too connected, by which I mean either they're too connected or it's just an edge. Okay, so that's the thing that we're going to aim for here. Anyway, we're going to have to prove a couple lemmas on the way in order to get there. So let me start. Let me do the following. Let me just cut this. And maybe I can bring that back later. But I'll keep the definition of block around. So again, by definition, a block is going to be a maximal subgraph of a graph of your graph G. And this maximal subgraph, I'll call it H, has to have the property that is connected and remains connected when you delete any vertex. And I'm going to now prove a couple of lemmas. So I claim the following. So first, I'm just, this is a proposition in the notes. I somehow feel like calling it a lemma now. So I claim that if H1 and H2 are distinct blocks, then they share at most one vertex in common. So you can't have two distinct blocks of a graph that somehow overlap on two vertices. And I think if you internalize these definitions well enough, it's kind of clear why that should be maybe even. Let's give a formal proof. So we'll go by contradiction. Suppose for a contradiction that doesn't happen. I love going by contradiction here because, again, it's giving me a picture I can draw. I suppose for a contradiction that there are two distinct blocks that overlap in at least two vertices. I can draw it. So let's suppose for a contradiction that that doesn't happen, that there are at least two vertices in H1 and H2. And what's our contradiction going to be? I've got these two pieces of graph that are, they're two connected or almost two connected in the sense that they just have two vertices. Now, what's going to happen here if they're sharing at least two vertices? Well, I claim that the union of those two is going to be even better. The union of those two is going to be connected, and is going to be connected when you remove any vertex. So let's suppose for a contradiction that H1 and H2 are overlapping in at least two vertices, and I'm going to define, I guess in the notes I call it H prime. I don't know why I called it H prime. So H prime is going to be H1 union H2, just the union of those two subgraphs. Now I claim that H prime is going to be connected and is going to stay connected when you delete any vertex. So my claim is that H prime satisfies 1 and 2. Right, if I can prove this, if I can prove that H prime satisfies both of these properties, then I have a contradiction, right? Because H1 and H2 were supposed to be maximal subgraphs of my graph G satisfying properties 1 and 2, and I've just enlarged, right? I've just found an H prime that I got by enlarging H1 or enlarging H2, and therefore that H prime is contradicting our basic assumption about H1 and H2 being maximal. So if we can prove this claim, that will give us a contradiction and thus complete the proof. So I need to show you that H prime satisfies properties 1 and 2. Well, 1 is automatic. If I give you two, one is a thing that we've said before. If I give you two connected subgraphs of a graph G and they share a vertex, then their union is going to be a connected subgraph of G. So 1 is a thing that we've previously proved. So the union of two connected subgraphs sharing a vertex is connected, and so 1 holds. How about 2? Well, let's take a vertex in H prime. So I have to show you that H prime is connected, and however you delete a vertex, H prime is going to stay connected. So good, okay, we've got it connected. Let's delete a vertex. So let's let V be a vertex of H prime. Now, what's going on? Well, let's look at H1 and H2. H1 has the property that however you delete a vertex from it, it will still be connected. So H1 minus V is connected. Here, there's a chance that the vertex V is not in H1. If the vertex V is not in H1, I'll just declare H1 minus V to just be H1, right? So if I give you a graph and you try to delete a vertex from it that's not in that graph, you just get the same graph back again as you would assume. So H1 delete V is connected. Similarly, H2 minus V is connected. But now I'm back to that same property. H1 delete V is a connected subgraph of G. H2 delete V is a connected subgraph of G. And those two subgraphs have to share a vertex, right? I mean, H1 and H2 overlapped in at least two vertices. I've removed V. Well, that's only removing one vertex. H1 delete V and H2 delete V are still connected subgraphs of my graph G, and they still share a vertex, and that means that the union of those two is connected. So H prime minus V, this is equal to the union of H1, delete V, union H2, delete V. And again, well, I'm not writing quite all the words here. There's a little bit more in the notes. But again, this is the same property as before. H1 delete V. H1 delete V is a connected subgraph of my graph G. H2 delete V is a connected subgraph of my graph G. Those two connected subgraphs overlap in at least one vertex, and that means that their union is another connected subgraph, and that means H prime delete V is connected, and that completes the proof of two. So we've proved that if you have two distinct blocks, then they can overlap in at most one vertex. Now, I'm going to prove something slightly different from what's in the notes here. It's a very similar argument. It's really not much different, but it will allow me to structure things a little bit differently. And I'm going to, again, keep my definition around here. Good. Okay. So we've proved now that if you have two distinct blocks of a graph, then they overlap in at most one vertex. What happens when they do overlap in one vertex? So suppose I tell you V of H1 intersect V of H2 is equal to singleton V. Right, so there it is. So there's this is a possibility. So I'm giving you two distinct blocks of my graph, and they're overlapping in the vertex V. Now, what I claim, and this is what we saw in our picture, when you had two blocks that overlapped on a single vertex, then that vertex that they were overlapping on, it's a cut vertex of the original graph. And when you remove that, you're disconnecting those. And that's what we're going to prove. So if you have two distinct blocks that overlap in a vertex, then V is a cut vertex of your graph G. And moreover, when you delete the vertex V from G, what's left of H1 and what's left of H2 are going to be in different components. And H1 minus V and let me say it this way. And in the graph, G minus V, so in G minus V, you're going to have a connected subgraph H1 delete V, and you're going to have a connected subgraph H2 delete V, and those connected subgraphs are going to be in distinct components of G delete V. So I just want to emphasize, in this graph, G delete V, H1 minus V, and H2 minus V are in different components. I'll say distinct. Right? So again, if I give you two blocks in a graph, we've proved that they can't share two vertices. Now I'm considering the case when they share exactly one. Suppose they overlap in exactly one vertex, and that is the vertex V. Now what I'm claiming is that in this case, that vertex V is going to be a cut vertex, and moreover, when you delete it from the graph, what's left of your two components, what's left of H1 delete V, and what's left of H2 delete V, those are going to be in separate components in G delete V. Right? So if you delete the vertex V, what's left of them will be separated. And this proof is also very straightforward. What's happening? Well, let's assume not. Suppose for a contradiction that this is violated. Let's suppose that we don't have this happen. Suppose for a contradiction that when you delete the vertex V, H1 minus V and H2 minus V are in the same component. Now, here's H1 minus V, here's H2 minus V. I know that they don't overlap in vertices, right? H1 and H2, they only shared the vertex V. So I've got what's left of them is in the same connected component. Well, that means you can find a path that goes from one to the other, right? So I can choose a path P so that one end of P is in H1 delete V, and the other end of P is in H2 delete V. And now I'd better draw a picture with what remaining space I have. So what's going on? So there was a vertex V here that we kind of cut out of the graph. Yeah, let me circle it right. So I'm going to remove V. And so this was H1 and this was H2. After removing V, we could then find a path in the graph that goes from H1 to H2. And if you want, you can assume that this path, if you take P to be a minimum length path of that form, then it really will look like this, right? There will be no internal vertex in here that's in H1 or H2, because that would have allowed you to shorten the path. So there's our graph, and probably you can see what's wrong here. This is really the same argument that we had before. In fact, if I was being super slick, I could have encompassed it in the original. Now, what's going to happen if you take the union of P and H1 and H2 in the original graph G, that is going to be a subgraph which is connected, remains connected when you delete any vertex, and it's larger than H1 or H2, and it's got by enlarging H1 and H2, and that contradicts our basic assumption that H1 and H2 are blocks. H1 is supposed to be a maximal subgraph of G that is connected and remains connected upon deleting any vertex. So there's a suppose for a contradiction. We're going to choose a path such one end of P is there, one end is there. Now I'm going to just say this because I'm running out of room. But now what I claim is H1 union H2 union P. This is connected and stays connected when you delete a vertex. So it's contradicting our assumption that H1 is a block, or contradicting the assumption that H2 is a block. I'll just say this satisfies and 2, and that's a contradiction. And I'll just argue that here in words for a moment. This is really quite straightforward. If I take this, I mean, there are a couple cases to consider here, but it's not a challenging thing. So I'm arguing that this subgraph stays connected. Sorry, I'm arguing 1, that it is connected, and 2, that it stays connected when you delete a vertex. Well, why is it connected? Well, H1 is connected, H2 is connected, they overlap in a vertex, therefore H1 union H2 is connected. P is a path, that is a connected graph. P overlaps, it shares a vertex with H1 union H2, and therefore the union of those two is connected. Right, now I have to consider what happens when you delete a vertex from this graph and argue that it will stay connected. And there are a couple cases to consider here. You could delete the vertex V, for instance. If you delete the vertex V, we are well prepared. In that case, H1 delete V is a connected graph. It shares a vertex with P. So that means H1 delete V union P is connected. And that graph shares a vertex with H2 delete P. And H2 delete V is connected, and therefore the union of all those will be connected, right? So, I mean, we've got this nice feature. If you take 2 connected subgraphs of a graph and they overlap, then their union will be connected. So we just have to verify that however you pluck a vertex out here, we're holding on to our connectivity. But I've got this nice feature that if you take H1 and delete a vertex from it, you stay connected, right? So H1 delete V is connected, H2 delete V is connected, P is always connected. And because these things overlap, their union will be connected. You could delete a vertex that's in H1, but it's not the vertex V. If you delete that vertex, say you delete some vertex, say maybe you delete some vertex over here, maybe that's the vertex U. Well, H1 delete U is going to be connected. H2 is connected. Therefore, their union is going to be connected. Now, that vertex U might or might not be the end of the path P, but it doesn't really matter. If you take a path and remove its end, you still have a connected subgraph, and the union and that connected subgraph is going to overlap with H2, and that means their union will be connected. So if you delete a vertex U out here, you're going to stay connected. You could as well delete a vertex. You could delete some vertex out here maybe, but it's much the same story. If you delete a vertex from the interior of a path, then your path is going to break into 2 connected pieces, but here one of them will join to H1 and the other will join to H2. And so again, I'm going to be left with a connected subgraph. So what's happening here is that our block structure here is really quite nice. If you have 2 blocks, either they're completely disjoint or they share exactly one vertex, and in that case, that will be a cut vertex of the graph that separates these things. Right. Okay. So let me go ahead and move to a new page. Right. So we've got our blocks in our graph, and we know that when they overlap, they'll be the vertex they share in common must be a cut vertex. Now, this allows us to make a big definition, and let me write this one out. This is called the block cut point graph. So I'm going to take a graph G. And for the moment, let's assume that G is connected and simple. Again, if I'd given you a graph that's not connected, well, you can just work within each connected component. And the assumption that the graph is simple is of no... this is just to clean up the statements. It's not really important. So I'm giving you a connected simple graph here. We're now going to define a new graph called the block cut point graph of G. The block cut point of G. So this is going to be denoted BC of G. This is going to be a bipartite graph. It's going to be a simple bipartite graph. And I'm going to tell you what the bipartition is. So the bipartition is going to be A comma B. And the rule is that A is going to be the set of cut vertices of the graph G, and B is the set of blocks of G. And the rule is that, so I'm doing a kind of funny thing here. So again, we start with the graph G. I'm going to make a new graph based on G. And this new graph is going to kind of be harnessing the two connected structure, the two connected pieces of my graph G. And this block cut point graph, it's got two kinds of vertices. So on one side are the cut vertices. On the other side are the blocks. So, well, I don't know how best to draw this. So, I mean, the block cut point graph, like a vertex over here is maybe I'll just sort of draw big vertices here. This might be like H1, and this is H2, and so on. But these are just vertices of the block cut point graph. And the rule, quite naturally, is that if I give you a cut vertex and a block, those are going to be adjacent vertices in my bipartite graph, in this block cut point graph, if and only if, when you go back and look at the original graph, that cut vertex I gave you is going to be in the block, a vertex of that block. So the rule, like so far I've defined, anytime I give you a graph G, we've got some set of cut vertices, we've got some set of blocks. I'm using those to define a new graph called the block cut point graph. And we're making a simple bipartite graph here. And I'm going to tell you the rule for adjacency here. And again, the rule is going to be that a cut point and a block are going to be they're going to be adjacent as vertices in the block cut point graph, if and only if, when you go and look at the original graph, that cut vertex was contained in that block. So the rule is that of a cut point, I'll just say A in A and B in B are adjacent if in the original graph, A is a cut vertex of the original graph, and B is actually, that little b is a subgraph of my original graph, right? That is a block. If and only if the vertex A is contained. Maybe I'll just emphasize if and only if. I mean, I'm giving you a definition here, so I can just say if. But so if in the graph G, the vertex A is contained in the subgraph B. Okay. Well, this definition has taken the whole page here, which is a little unfortunate because I therefore don't have the space to keep it around. Let me just sort of take a moment and kind of digest and process this. Now, again, this is a kind of derived object. if I give you a graph G, they're the components of G. That's a natural structure that we get. I'm now going to be describing another kind of higher order structure that's going to keep track of the ways in which our graph is kind of two connected. And I'll warn you in advance, or perhaps just comfort you in advance by telling you that this same thing doesn't really continue on up to higher connectivities. So this levels up very nicely. Understanding two connected pieces of a graph is really natural, and this is the structure that does it. But once we get up to kind of higher kinds of connectivity, this same simple kind of construct really goes away. So we kind of have connected components that tell us, well, which pieces of the graph are connected. And we have this block cut point graph that's going to kind of be telling us about the two connected pieces of our graph. But there really aren't higher order analogs that are very nice. So now the probably the best way to get a handle on this definition is actually to see how it works. Yeah, I think I'm going to have to erase this page to draw anything. So again, I'll just emphasize. So we're starting with the graph G. We're going to make a new kind of derived object from it, the block cut point graph. It's a bipartite graph. You've got vertices on one side, blocks on the other, and you're going to have an adjacency in this bipartite graph if this vertex is contained in this block. So let's see an example. Let me just get a new page here. Can I just paste that thing? Yeah, there we are. Okay. So here's my graph G, and let's let me make some labels. So I'm only going to label the things that I care about here. So I care about cut vertices and blocks at the moment. So this is going to be the vertex V1. Actually, let me maybe for simplicity, I'll just use numbers. This will be 1, 2, 3, 4, 5, 6, and 7. Those so the yeah, I got them all. Yeah, sorry. Okay. So those, I'm just labeling those vertices 1 through 7, and I'm going to label these blocks, right? So in orange we have the blocks, and let me just use letters of the alphabet for these guys. So this will be A, B, C, D, E, F. Oh, unfortunately, I don't want to use G. H, G. I'll use J. Okay. So anyway, there are some subgraphs. Those are blocks of our original graph that I am I'm naming with some capital letters. Okay, so the block cut point graph is going to be a graph whose vertices are, if it's going to be a bipartite graph with two kinds of vertices, you're going to have all the cut vertices of the graph G on one side and all of the blocks of G on the other side, and the natural kind of adjacency. So a block is going to be adjacent to a cut vertex in my block cut point graph if in the original graph that block contains the vertex. So this is a super loaded thing to say, but it's actually very simple. So what are we going to do when we make the block cut point graph? I'm going to draw it in a little bit of a funny way over here. But maybe it's not so funny at all. So here's D, here will be C, here will be E. Here will be H, and here will be F. E is also joined to J, or G is, okay, and here's E, and there's 2, there's B, and there's A. But those are just the vertices on one side of my bipartition, right? We also have what? Well, there's the vertex 7 over here, and I've got the vertex 6. I've got the vertex 4. And there's the vertex 5. Let's see. Let me add one more thing to my picture just to add a little bit of extra complexity here. I'm going to add one more edge coming off here. And that's going to give me one extra component, one extra block. This will be the block K. Okay, 5, 2, 3. This may be, anyway. Well, this is what it is. I'm now going to draw in the graph. There's the graph. So, what is happening here? I mean, hopefully you can kind of see how I got to this thing. You see that, I mean, really, this block cut point graph, it is a very, very natural object. I mean, when I take my original graph G and I just circle those blocks, I mean, you can see that there's a kind of tree-like structure to this to this picture, right? I mean, if you want to just sort of think of the block as just being a single vertex, then there you go. You're staring at something that's like a tree. And really, one way of describing it, so we are getting a tree here. Our block cut point graph is a tree, and one way of describing what we're doing here is we're kind of take each block and just turn it into a single vertex. And if that block was going to be adjacent with 3 cut vertices, we'll make a vertex for it that just joins to those 3 cut vertices, right? So another way we could kind of describe constructing the block cut point graph is we could take our original graph, just keep all the cut vertices there, and then anytime you have a block, just lift up the block, we're going to throw it away and replace it by a new vertex and just join that to each of the cut vertices that block contained. That would also give you this block cut point graph back again. So again, for our graph G, this is going to be the block cut point graph of G. The block cut point graph of G, it's a bipartite graph with 2 kinds of vertices. On one side, you have the cut vertices of the graph G. On the other side, you have the blocks of G. And the adjacency rule is kind of the natural one. A cut vertex is going to be adjacent to a block if, when you go back and look at the original graph, that cut vertex was contained in the block. So this is the graph G. This is our block cut point graph of G. And again, we think of the block cut point graph of G. This is really kind of harnessing the 2 connected pieces of our graph G. And now our main theorem here is, this is an observation. I don't know why it's an observation, but anyway, I'm just gonna call it a theorem. Is that if G is connected, and you could say simple. I'm just sort of assuming the graphs are simple. If I give you a graph that's not simple, the block cut point graph is the same as it would be if you threw out the loops and parallel edges. So if G is connected, then BC of G is a tree. So if I give you a connected graph, the block cut point graph is always going to be a tree. Now, the proof of this is really pretty quick. So let me prove some of it. Let's first observe that if I give you a cut point then it is going to be incident with, it's going to be connected to some block. And I'm just going to draw the picture for you here. So suppose this is a cut vertex, and when you delete it, you have two different components. So that means in the original graph, you have to have this. Maybe there are more. Well, in this case, this edge and this edge, this edge that I have here is that is a graph that is connected and has the feature, just that edge on its own. It's a connected graph with the feature that however you delete a vertex from it, it stays connected. So that means that edge, it has to be contained in a block, and it's going to be contained in a unique block, right? Every edge of the graph is contained in a unique block just by our first observation, right? If you weren't allowed to have two different blocks overlapping on two vertices. So every edge is going to be contained in a unique block of the graph. And you can see that you can't have a block containing these two orange edges that I've just drawn. If you had a block containing those two, well, when you delete this that vertex in the middle, you'd be disconnecting them, right? So this means that every cut vertex is going to be is going to be adjacent to a block, and it's very easy to see that for any two blocks in my block cut point graph, you can walk from one to the other in the block cut point graph. Why? Well, if I give you two blocks, just choose vertices from those two. My original graph is connected, so I have a path that goes through. As you move through that path, well, as you move through that path in the original graph, you're either staying within a block or moving from one block to another along a cut vertex. So whatever that path does in the original graph, you can just basically mimic it. You're just walking along. Each time you move in the original graph, you're making a move in this block cut point graph. So my block cut point graph is clearly going to be a connected graph. Why is it a tree? Well, suppose not. Suppose it weren't going to be a tree. Well, then you'd have to have a cycle, right? So that would be some cycle. That would be I'm just going to draw a picture. So that what would a cycle look like? Well, it would be a block in the original graph, then a cut point, and another block, and another cut point, and block, and cut point around. But what that looks like is this. Right? You'd have to have some picture like this where, you have to have a cycle in the block cut point graph. We have a bipartite graph. So the vertices of that cycle are alternately cut vertices and then blocks, right? So you've got cut vertex, cut vertex, cut vertex, and so on. But this would contradict that lemma that we just proved, right? So in this case, when you look at, in this case, the union of all of these so-called blocks would be a connected subgraph of the original graph, and would have the feature that however you delete any vertex, you're going to stay connected. So this block cut point graph, it contains all the cut vertices, it contains all the blocks. We have this natural adjacency. We've seen that every block is going to you can walk between any two blocks. Every cut vertex is connected to some blocks. This means that the graph is going to be a connected graph. We also have the feature that this connected graph cannot possibly have a cycle, and that means that this graph is a tree. So our block cut point graph is always going to be a tree, assuming we fed in a connected graph. And and again, this block cut point graph, it's really a nice and very, very natural object. It's a level more complicated than just connected components, but it's not all that hard. Trees are pretty nice graphs after all. And this block cut point graph, it is always a tree, and it's harnessing these, kind of the two connected pieces of the graph. It's telling us what those things look like and how they join to one another. So the block cut point graph is going to be a really useful structure for us. And that's the point of this lesson, and so I will stop there.